Lecture 5, Module 2, Measure Stage Part 2, Distributions. The topics covered in this lecture are Measure the Process. Last time we looked at first pass analysis and time series plots and histograms, and this time we'll be looking at distributions, the normal distribution and some of the other distributions. Data behaves in a lot of different ways, but fortunately data tends to follow some well-known and well-understood behaviors that we have mathematical models for called probability distribution functions, and this makes it easier to analyze our processes. The first step in the Six Sigma process is to fit your data to probability distributions, as this is critical for making decisions and for accurate prediction of future performance. So we need to understand these mathematical models a little bit so we can use them effectively and correctly. A probability distribution is a function that describes the probability that a random value will have certain values. For continuous random variables, they are referred to as probability density functions, which provide the probability for each possible value in the distribution range. The normal distribution, or Gaussian distribution, or what's commonly called the bell curve, is the most common statistical distribution for continuous data, since many physical and chemical and biological measurements exhibit this behavior. Most of the statistical analyses discussed in this course require that the data come from normally distributed populations for the analyses to be valid. Now below is a graph of 100,000 points of data that were created that exhibit a normal distribution. Minitab has the ability to create random data, and random data was created with a normal distribution and then plotted. And sure enough, it looks like a normal distribution. Now, histograms of normal distributions don't always look exactly like the normal curves, like look at the histogram below. Minitab will draw a curve based on the mean and standard deviation of the data to fit over the histogram, and below is a graph of 100 data points from a normal distribution with its corresponding normal curve drawn over it. Now, the bar graphs, the bins, look like they're normally distributed. However, the bin between 100 and 104 has a bit of a spike to it. And then the bin at 88 and the bin at 112, a little bump up on the ends. But for the most part, the data looks like it's normally distributed, and it seems to be fitting underneath the curve. But it doesn't look exactly like it's normal. Now, continuous data may also take on different shapes, but still be from a normal distribution. Normal data can be skewed to the right, and this is typically seen where there is a natural lower time boundary or some kind of limit boundary. In this case, such as days for a completion of a change control. So the lower boundary would be 0 days. It can't be done in less than 1 day or less than 2 days, so there's no way the data can go down there. But it can very easily skew off to the right and go up to 30 days, 60 days, 100 days. So who knows how long it could take. But on average, they'll be clustered down around 6 to 5 days. You'll just never get any data that's going past the 0 point. So the data will look skewed to the right. And the normal data may be skewed to the left, and this is typically seen with a natural upper boundary or time limit. Now in this case, such as for total cases in an 8-hour shift. There may be some natural boundary where you cannot possibly make more than 105 cases in a shift because the equipment doesn't move that fast. That's the upper maximum limit for the cases. But you can always make less. In fact, you can make 0. If the production line breaks down, is down all shift, you're going to have 0 cases for the 8-hour shift. But on average, most of the data will be up around, let's say, looks like around 100. But you'll run out of time before you can ever get up to 105 because the machine doesn't work that fast. So the data will be skewed to the left in this case. But it actually is coming from a normal distribution. Continuous data may also demonstrate a relative peakness of the data or a flattening of the data, and this is called the kurtosis. Data from a normal distribution should have a kurtosis of 0. Data that is peaked will have a positive kurtosis. As we see here, the bin between 99.6 and 108 is very pronounced. 40% of the data is packed into that bin. So there's hardly anything on the left and on the right. Most of it is all in that one area. And data that is flattened will have a negative kurtosis. As you see, the data is distributed around 100, out to 120 and down to 80. Quite a lot of it is shared in those bins. So it does look like it's normally distributed, just flattened out a bit. Now, many processes follow probability distributions other than the normal distribution. And some of them look very much like the normal distribution, or like right-skewed normal distributions. So on the right, we see in the upper right-hand corner the histogram for log normal data, and below that the Weibull data, and below that the exponential data. And they all look alike. They look like right-skewed data in appearance. All the way to the left, we have the Poisson data and the binomial data, and again, they look like right-skewed data. And in the center, we have the logistic data. It looks normal. And then below that, the strange-looking uniform distribution, where the data is uniformly spread throughout all the data points, and you get the flattened-looking peaks. So how do we tell the difference between these different types of distributions and our data when they look so much alike? Well, one way to tell the difference is to understand the data type we're dealing with and the type of process we are trying to get the data from. Data from probability distributions other than normal distribution may involve attribute data, for instance, or maybe measuring failure rates or reliability rather than process output. So let's look at the binomial distribution. This is used to describe processes where the results have one or two possible outcomes, and that's where the name comes from, binomial, bi2, nominal name. For example, a package off a packaging line either passes or fails an inspection. Distribution uses nominal data, so it's pass-fail. And as you see, it has the probability of picking failing items using samples of 25 from a population of 100,000 with a defect rate of 9, as on the left, and the chart on the right shows probability using samples of 100. Notice how the distribution now looks like a normal distribution, slightly skewed to the right. So we may think this is normal data and be treated that way, but we should consider the type of data that we're collecting. The Poisson distribution is used to describe the number of times something can occur in a finite described space. For example, a Poisson distribution can describe the number of defects in a medical device or the number of calls that are coming into, let's say, an adverse event call center. The Poisson distribution has only one parameter called lambda, which is equal to the mean and the variance. Note again, as n increases, the Poisson distribution approaches a normal distribution in its appearance, even though it's not. Again, we need to know what kind of data we're dealing with. The Poisson distribution and the binomial distribution both use counts of events as data. However, the binomial distribution, the data is limited to the number of trials. So however many packages you selected, that's the total number. So you can either have if you have 100 packages, you can have 100 passes, or 50 passes, 50 fails, but no more. The Poisson distribution account data is basically unlimited. So if you're examining a medical device and you're looking for defects, there may be 3 defects on a medical device, or there may be 1,000 defects. So it's unlimited. You look at 100 of them, there may be 1,000 on each one of them. So the numbers can be much, much higher. The log-normal distribution is related to the normal distribution. One special difference, it's the logarithm of the data that is normally distributed. And that's where the name comes from, log-normal. So on the left, we see a histogram of log-normal data, but on the right, the logs have been taken and the logarithms have been taken and plotted, and sure enough, they look like normally distributed data. Now, data that is log-normally distributed can be easily transformed into normally distributed data for analysis using the regular statistical techniques for normal distributions, and that's a legitimate thing you can do. So if you find yourself with this type of situation, you can always convert the data and perform your magic with these statistical analyses, and then convert back. Exponential distribution. This is used to describe components that have a failure rate that is constant, for instance, radioactive decay. The exponential distribution has applications in the pharmaceutical industry in analyzing the occurrence of endotoxin levels, impurity levels in APIs, or the reliability in medical devices. The Weibull distribution is used to model time to failure data. For example, a process supervisor may be interested in calculating the probability that a piece of process equipment will fail after 1, 2, 3, 4 years, whatever you may be interested in. And the Weibull distribution is described by 3 parameters: the shape, scale, and threshold. Now, depending on the values of the parameters, the Weibull distribution can take a variety of shapes. In the chart below, the Weibull distribution appears similar to an exponential distribution, but if you change the values, those values, you may see it look more like a skewed normal distribution. So again, knowing the type of data you're collecting and what you're looking at, what kind of system you're examining, is important in interpreting what type of probability distribution you should work with. The logistic distribution follows the S-shaped or sigmoid curve that is typically seen in the growth of populations such as bacteria or cells. mammalian cells. For such populations, the initial stage of growth is slow, then becomes exponential, and as the resources are depleted, the growth slows down again, forming that familiar S-type shape. This distribution is commonly used as a growth curve and is often used in biostatistics. Note the similarity in appearance to the normal distribution. Often we will be dealing with relatively small amounts of data, not 100,000. And the histograms we generate, while valuable and useful to look at, may not look like they're from normal distributions, even if they are. We may also not be sure if the data should be treated as normally distributed. So if we're dealing with data where we're not sure how it is behaving, one of the first things we should do is perform a normal probability plot. Below is a normal probability plot for the normal data from slide 4. Minitab can create a theoretical normal distribution in the form of a straight line and then plot your own data against it. If your data is perfectly normal, it will lie on this line. Any deviations from the straight line pinpoint data does not following the normal distribution. Now, Minitab will also measure the goodness of fit for your data against the theoretical and report a p-value or probability value for the data. If the p-value is less than 0.05, less than a 5% chance, then you should not consider the data as coming from a normal distribution, and performing any kind of statistical tests designed for normal distributions on it may be very risky, but I'll point out that that's not always necessarily the case. There are exceptions to that. Here we see the p-value is equal to 0.433, which is considered very good, and it is safe to consider this data normal. Notice, though, that these are 100,000 values from normally distributed data plotted against on a normal distribution, but the p-value did not come out to a 1.0. It's not 100%, 0.43, so it's only 43%. You will never see values of 100% or 99%. It's very rare. So once you get above 0.05, 0.25 or something like that, that's looking very good. Below is a normal probability plot for the data skewed to the left from slide 14. Notice the data turned up at the upper boundary and the p-value less than 0.005. Doesn't look good. And below is a normal probability plot for the data skewed to the right from slide 14. Notice the data turned down at the lower zero boundary and the p-value less than 0.005. And here is below is the normal probability plot for the data with positive kurtosis from slide 15. Notice the S shape of the data and the p-value of less than 0.005. Very little of the data is actually within the lines there where we expect it to be. And below is a normal probability plot for the data with negative kurtosis from slide 15. Notice this data fits fairly well with a p-value of 0.210. This data is normal enough, and you can feel comfortable performing normal statistical analyses or statistical analysis for normally distributed data. Now below is a normal probability plot for the exponential data shown in slide 21. Notice that virtually none of the data fit the line and the p-value is less than 0.005. Clearly the normal distribution is a bad fit for this data. Do not use it. If our data does not fit the normal distribution, we can try plotting it against other types of probability distributions. Here is an exponential probability plot for the exponential data shown in slide 21. Notice that now virtually all the data fit this line and the p-value is now 0.117. Again, not perfect. Our data fits this distribution well enough. If our data is not normal, or we are not sure what type of distribution our data is from, the next thing we should do is perform a distribution ID plot. Minitab offers the ability to analyze our data against 15 common probability distributions to see which distributions the data most closely matches. Now the following slides show the results of analyzing the 100,000 data points created in a Weibull distribution shown in slide 14 against these 15 different types of distributions. So here we have the first plot, a 4-pane plot from Minitab, which shows a normal distribution with Box-Cox transformation, the Lognormal, and the 3-parameter Lognormal. As you see, there aren't good fits for any of these. The p-values are all less than 0.005, except for down at the bottom of the 3-parameter Lognormal, you see an asterisk. When you see an asterisk reported by Minitab, that means a p-value cannot be calculated for this distribution. So none of these fit. Now we look at the exponential, 2-parameter exponential Weibull, and 3-parameter Weibull. notice that the Weibull fits, and the Weibull and 3-parameter Weibull distribution are very, very well. But also, if you look up at the exponential and the 2-parameter exponential, you'll see 0.25 and 0.405. So our distribution fits the exponential and 2-parameter exponential also very well. So which should we use, the Weibull or the exponential? Again, as I said earlier, knowing the type of data and the type of process values that you're analyzing is important in figuring out which distribution is appropriate. Then there are ones called the smallest extreme value, largest extreme value, the gamma and 3-parameter gamma. Again, looking at this, you'll see that the gamma is 0.239 p-value, so it looks like it fits there pretty well. Once again, knowing what the gamma is versus a Weibull, which one should you be choosing? And also the logistic, log-logistic, and 3-parameter logistic. So none of these are good fits. Luckily, we will be dealing with the normal distribution most of the time.